sweeping matrix. This matrix is a transformation that acts upon an arbitrary trial vector here and turns it into a swept trial vector on the left. What is done essentially is to ignore the first component in your arbitrarily chosen trial vector, since there are zeros in the first column of the matrix. So basically that one's thrown away, and then the swept vector on the left is formed by proportionally taking terms of the u2, 3, 4, and 5 up through un that you had arbitrarily chosen. The first equation that we found then was an equation for the first component of the trial vector in terms of other components. And these coefficients that we discussed take these positions, and they reflect the direction of the first eigenvector. The other columns here show units in the main diagonal and directly map the components of this swept vector, namely u2, u3, on down to un, directly from your trial values. So it's an interesting process in which you put the arbitrary vector in here. The method throws away your first number but replaces it with something very carefully chosen to make this vector then swept of all content of the first eigenvector. One way to do this is shown in the bottom, where you introduce the sweeping matrix on the left side of the equation. Then, as this equation is iterated, you'll find that your trial vector, originally put in here, will be swept. The improved vector calculated, brought back in here, and it will be swept again. It needs to be swept on each cycle so that you never, through round-off error, develop a growing amount of that unwanted but dominating first vector. A natural worry might be that the sweeping matrix would affect the convergence process in some way. I'll just give a heuristic argument that as you start to converge towards, say, phi2, the second eigenvector, then we know that phi2 is orthogonal to phi1, and so the sweeping matrix does less and less as you converge to the right answer, and in the limit does nothing at all to the trial vectors that you're iterating. Another comment is that because of the way that matrix multiplication is associative, we can multiply the first two matrices rather than doing the sweeping operation separately. And what that does is then to build the sweeping matrix into the transformation matrix A. Together I'll call it a dynamic matrix number 1, which not only has the structural properties in it, but also sweeps out the first eigenvector, so that you do not need to continually sweep. In fact, you build it right into your transformation matrix, so the sweeping is automatically carried out. Flamenhoff's contribution to this method was to show that as you did sweeping for more and more modes, that this could be done in a nice organized way with sequential mappings. So that if you wanted, for instance, to solve for the m plus first mode, let's say, then you would have orthogonality conditions on this trial vector being orthogonal to the first mode, to the second, and on up through the mth. Now he showed that there were matrices S1, S2, on up through Sm that could be multiplied together to give that effect. Those could be absorbed into the dynamical matrix, again called D sub m, which would then sweep out all of those undesired modes in question. This allows you then, in principle, to get all the modes in the problem by sweeping perhaps from the largest one on down, or conversely the smallest one on up. In fact, in practice, it's found by commercial code developers such as the McNeil-Schuyler Corporation that usually sweeping for about 6 such modes at a time is about the best you should do, and then you need to do a shift after that. Let me make a few comments about the power method. This method is old-fashioned, but it's useful for learning because it builds intuition. The method isn't strong enough to be used commercially, but it can be used in moderate-sized problems, perhaps a couple hundred degrees of freedom, and you can get the first 20 or so natural frequencies by sweeping and by shifting. If there are repeated eigenvalues, the method fails because of the eigenvectors that correspond to that repeated eigenvalue. They span a certain space. Let's suppose there are 2 repeated eigenvalues. Then you have 2 eigenvectors that form a plane in some n-dimensional space. They have the same stretch factor when the transformation matrix is applied, therefore neither of them can dominate the other. And a trial vector will unfortunately then wander in that subspace, unable to decide between those 2 competing eigenvectors. That can be fixed, however, and it has been fixed, for instance, in the inverse power method in the commercial codes. The method is best for the flexibility formulation because that naturally gives the smallest frequency and the smallest buckling load. Had the stiffness approach been used historically first, then the method wouldn't have been as useful. We've discussed the power method here just for the special eigenvalue problem. I call it opposite, maybe I should put that in quotes, but it's different from the inverse power that we will discuss in our next lecture, in the sense that the inverse power method converges to the closest eigenvalue to the shift point rather than the farthest. That may not sound like a big difference, but it really is important. Finally, when you're choosing trial vectors, perhaps when you're sweeping, it's good to remember that the almost converged vector from the previous sweeping iteration would contain a dominant amount of error in it that would be the most stubborn, unwanted eigenvector at that stage. However, when you move to the next sweeping, then you would want to enhance that, what was previously a contamination, and bring it out. So it actually makes sense to use an almost converged eigenvector from a previous iteration process to find that most stubborn, unwanted vector, which is the dominant contamination in that process. I've mentioned that Rayleigh, more than 100 years ago, realized that approximate solutions to vibration problems often led to frequencies that were too high. The reason being that any error that you had tended to cause greater energy to be absorbed. Originally, that idea came about in the potential energy solutions and had to do with a lack of degrees of freedom. We have something comparable here, though, when you iterate, in that if you're trying for the lowest frequency, which is a common situation, that you have an answer that has an eigenvector that's near convergence, but it's contaminated with higher mode content, and therefore they correspond to higher frequencies. So in this case, you would find that you approach the wanted eigenvalue, which is one of the extreme ones, say the smallest, from above in that case. If you're trying to get the largest eigenvalue, you should approach it from below. In other words, it's hard to get an answer that's super perfect, that lies on the other side of the modal and frequency content in the problem. For the sample problem that we discussed earlier in the lecture, we had the matrix shown, 2, 2, 2, 5, an unknown displacement vector, an eigenvalue, and then the displacement vector again. In this case, this will converge to the largest eigenvalue. And the claim is that if you use the Rayleigh quotient, which is really the best available estimate of the approximate eigenvalue, that in approaching the eigenvalue 6, that you will approach it from below. Now, when we did our original work on that, we found that our first estimate of that higher eigenvalue was 7. That was found on the basis of a unit normalization where we divided out by that component. Basically, you were getting information only from that component of the problem. I'll just list the results from the successive iterations. The second iteration gave this vector, the third iteration gave this vector, and ultimately, after many iterations, you reach the exact answer. This star is meant to imply the exact answer. Now, if we would apply the Rayleigh quotient for our special eigenvalue problem to each of those iterations in sequence, putting in the first, second, third, and so on here, then we would get the set of numbers that I'll show on the next page. Let me show the first calculation for the Rayleigh's quotient explicitly. This will be the one from our first iteration, and here was the vector that we found, entered both on the left and the right side. Then in the denominator in both sides. Here you have the multiplication following this product, giving this vector. Then you do that inner product and get 7.9 over 1.3. That leads to an eigenvalue shown here, which is a little lower than the exact value of 6. The second iteration, when you use the Rayleigh's quotient, comes out 5.9997, and look how fast that's converging now. I'll just add the third one here, which came out to all 5 significant figures, so you certainly have as much accuracy as you'd need from the iteration side of the process. Other data in the problem are not as accurate as 5 significant figures, such as Young's modulus, all the material properties and dimensions and so on. So it really doesn't make much sense to carry the process a lot farther than that. So the convergence happened very quickly, and when you use the Rayleigh quotient, the problem converges from below. Now let's do a calculation of the power method with shift. I've taken a new matrix here, and it has some non-integer eigenvalues. This is a special eigenvalue problem, since the matrix in this location is the identity matrix. But first I'm going to ask for eigenvalues by the classical determinant method. You'll see how that goes in a minute. Secondly, we'll use the power method with shift to find the eigenvector corresponding to the lowest eigenvalue of the system and carry out 2 iterations. Remember that to get the smaller eigenvalue, that's not easy for the power method, and so we have to shift up beyond that one so that it will converge to the smallest eigenvalue. The determinant method is a classical method, and that will provide us with our baseline solution. The equation of the coefficients of the matrix here is that the determinant of the coefficients must be 0. We combine our matrices together because of that distributive property. We find this set of terms. This is a quadratic equation. We have to collect terms, use the quadratic solution here, and you get 51 plus and minus some terms here. Turns out to be 25.5 plus or minus 25.005. And then these become the eigenvalues. One of them is rather large, the other one is moderately small. So on the real number line with the origin here, we've got one fellow sitting right here and the other one way out here somewhere. So if this is the, call it the lambda line. So we're going to need to shift away from the origin out far beyond that first eigenvalue, hopefully toward the second one, in order to emphasize the first eigenvalue and to find it with the power method. We'll arbitrarily pick the shift point clear out by the second eigenvalue. Let's say arbitrarily p equals 51. And on this plot of the frequency spectrum here, our first eigenvalue is at the origin, and then we'll put our shift point out a little beyond the second eigenvalue. We have our basic equation here. We'll combine the terms, get this dynamical matrix, and then we'll start the iteration by assuming the 1, 1 vector here. So this is our trial vector shown on the right. Then we carry out that operation and you'll get minus 45 and plus 4. Something unusual happens on our first cycle. I'll normalize the trial vector to give it a unit maximum value by pulling out the 45. And then by comparing the left and the right sides here, we see that the shifted eigenvalue is minus 45. So that's the unusual thing about getting a negative eigenvalue. That's not a physical one, though. We recover the physical eigenvalue by taking the shifted eigenvalue and adding in the shift p, which was 51 units. So we end up with a predicted eigenvalue of 6 as our smallest eigenvalue. Now, that's more than 10 times too high, since the actual eigenvalue is around 1/2. So we have a lot of error remaining in our problem after one iteration. Well, we don't give up hope. Here we take the normalized vector and put into the left side of a next iteration and carry out the multiplication. We collect terms in the eigenvector, and then we extract the largest component, which gives us the normalizing factor. That becomes our improved estimate of the shifted eigenvalue, and we get 50.44 with a minus. When we solve for the physical eigenvalue by adding in the shift, we get plus 0.556. Now that's looking a lot better, but it's still 12% high. We'd be better off to be using Rayleigh's quotient at this point for an improved value. The vector looks like this, and roughly 1 unit in the horizontal direction and minus 1/10 unit in the vertical, as shown in the sketch of the vector. From our determinant solution, we got the eigenvalue. We could have shown a solution for the eigenvector as well, and so these will be the fully converged values. The eigenvector is actually in pretty good shape, even after just the 2 iterations shown above, about 0.1% in error. And I don't know what the eigenvalues accuracy would have been at that point using Rayleigh's quotient, but would have been probably that good or better. Most often the eigenvalue is converging faster than the eigenvector when you do evaluate with Rayleigh's quotient. I'd like to do a numerical example of sweeping now. We'll take our standard problem that we've studied before, and we know what the answers are. The highest eigenvalue is 6, and the corresponding eigenvector is shown here and is plotted in blue in the sketch. We know that if we have that answer in hand, which would have happened naturally with the power iteration without any modification, then we would have these two in our hand. So now the question is, can we create a sweeping matrix D1 and solve for the second eigenpair? We would expect that to converge to the eigenvalue of unity and a vector that's perpendicular to this blue one here. Well, let's go through the formal process. We can guess what the answer is, unfortunately, because my problem is only 2 degrees of freedom. So we know that the vector direction is a dashed line, but we're not going to exploit that explicitly. We're going to just use the constraint equation here, which says that the new trial vector here should be orthogonal to the known first vector here. So that equation written out in scalar form is shown here. Then we solve for the first component of the trial vector in terms of the second. Those coefficients can be built into this law here and give us this sweeping matrix. We put the sweeping matrix in the position on the left side to modify an arbitrary trial vector such that it will be swept to give a swept vector, but actually we absorb these 2 matrices together, as is common practice, to give a swept dynamic matrix. Now we're free to put in an arbitrary statement for the assumed eigenvector. I've said we won't exploit the inside information that we have in this reduced dimension space. By that I mean I'm just going to take an arbitrary vector here as our trial vector. When you multiply by the dynamical matrix with sweeping embedded in it, you get this improved vector. When we normalize, that shows that the eigenvalue at this iteration is -2, which is non-physical, but okay for now. And then we get this eigenvector. The eigenvector turns out to be exact, in fact. And we see that by one more iteration by putting the normalized eigenvector into the equation of motion again, pre-multiplying with the swept dynamical matrix, and on the right side carrying the symbols, then factoring out the largest component, which is unity, we find that the eigenvalue is 1, and this eigenvector that we've used already is perfect. So we ended up with an exact answer after 2 iterations with a unit eigenvalue and the exact eigenvector. So that ends our lecture. The inverse power method is a very strong method for iterating the eigenproblem and finding solutions. It provides both the eigenvalue and the eigenvectors. It's a little more complicated than the power method that was discussed in the previous lecture, but still it's straightforward enough to allow the viewer to understand the convergence proof and to see the shifting and sweeping. There is a further method called Lanczos method, which is even more complicated, more powerful, and harder to understand. And in the lab that we do, we have the ability to run that particular solver. But I like to clear up this inverse power method and show you exactly what it is. I'll review the notation in the next figure. We'll review the power method. Then I'll discuss the inverse power method along with shifting and sweeping. We'll do a numerical example. And then, when you're sufficiently battle-hardened, we'll do the convergence proof. We'll end up with several problems in our problem session. I'll just write down some of our symbols that we use just to refresh those in your memory. K being the convention for the stiffness matrix of a structural dynamics problem, and M the mass matrix. The displacement vector with U as an upright character is the nodal displacement vector. This W is an unnormalized displacement vector. It comes out as an intermediate step in our iteration process. When I use a superscript S as shown, then that shows that you're iterating and you're on the Sth iteration. The eigenvector that results, as shown here, might be the ith eigenvector, for instance, the 7th eigenvector. If it's being iterated, it will have, in addition, the superscript as above. The lambda here is the eigenvalue, the lowercase ith eigenvalue, that's the physical eigenvalue. The cap lambda is the shifted eigenvalue. Let's review the power method for a minute. For the special eigenvalue problem, it's relatively clear that you operate with the matrix on a trial vector and the process goes from left to right here. There's no inversion of a matrix involved. K times U, where U is the nth iterate, will yield a vector which can, by proper normalization, be put in the form on the right. The s plus first iterate then is an improvement over the previous iteration step. Now if I explicitly write out the intermediate vector that's obtained, and think of this as a bunch of numbers here in the stiffness matrix and a bunch of numbers in the displacement vector, then this W is a vector of numbers. Over here, however, think of these as symbols on the right with a lambda and a u, and your idea is to try to equate those to identify what this eigenvalue should be. It's typically done by normalizing such that you have the largest component of the u vector serving as the reference, and when that is factored out, then the largest component is unity. At that point, you can identify then that the scale factor involved would be your improved estimate on the eigenvalue. That would be your s plus first estimate on the eigenvalue. Now this does converge. This process converges to the largest eigenvalue, lambda n, of the matrix K and its corresponding eigenvector. The way that we have found the eigenvalue here is a little bit rough in that it only uses the information from one physical component of the vector, namely the largest one, and to some extent the relative size of the rest of the pack. But that's not as accurate as if you were to use a Rayleigh quotient for your estimate of your current eigenvalue. So that would be your s plus first iterate. So it's recommended, if you really want an accurate estimate, to use the Rayleigh quotient. The inverse power method works in a similar way, but the matrix is first inverted. Here, when you had a physical problem such as this, which is the special eigenvalue form, you would then invert the K matrix, put it on the other side. At this point, it's helpful to move the eigenvalue lambda to the left side, and then this process, when iterated, will go from right to left in that